It turns out around I think it's about 4 or 5 Tesla, you start to, if you immerse a human being in 4 or 5 Tesla magnetic fields, they start to hallucinate quite
Oh yeah,
badly.
because we're diamagnetic, I would imagine that would have quite some effect. And at some point you start floating like a frog.
Yes, you start floating.
So how do you extract the power or the useful energy? It's very interesting. You mentioned that 4/5 of the energy is lost by neutrons. So how do you get whatever is
Yep.
left over and then convert it to electricity before it gets any further?
Yeah. So let's start with the neutrons, actually. Well, let's start in general. In fact, there's a paper, in fact, I'm writing right now about this. So it turns out there's a great simplification in fusion, and it also comes to be about its challenge, is that fusion by definition requires isolation and confinement of the fuel itself, and it's a volumetric process. So whatever you use in fusion, there's a volume of something making fusion, right? And there can no be zero terrestrial objects inside of that volume. So you just think about this from a high level point of view, you realize, oh, all of fusion has a volumetric source, and then there's a surface, an engineered surface around it that is the place where every joule of energy must come out. Yeah. So that varies in the different concepts, but that's where the engineered component is. So you can just think of this then as an areal power density, that namely there's a amount of power per unit area which is being pushed out to those two things. And so let's go back to the DT fusion. So this varies extremely significantly between the two different kinds of heat that are coming out, or energy that are coming out. So let's start with the alpha particle. So the alpha particle, remember, that's the concept. The alpha particle has charge, it's contained in the plasma, but it actually just thermalizes, it just gives its net energy. So imagine the plasma is at 10 keV, it's at 3.5 MeV. So it's like 300 times more energetic. So it gives its energy back and actually just ends up slowing down and becoming thermal with the rest of the plasma. So then we just, so what does that mean is that the heat goes in, the energy ends up as heat in the plasma. So that means it's how the plasma, which is just this collection of Coulomb of charged particles, touches this extended surface around it and transfers energy into it. So this is something called, so when plasmas touch solid objects, this is called a sheath is formed. It comes about, it's the negotiation that happens between the fourth phase of matter and the first phase of matter. So this happens in all low temperature plasma, anything that you have. And what it actually ends up being is it's an electrostatic barrier which is formed by charge separation in the plasma medium itself to actually enforce ambipolarity at the surface. Ambipolarity just meaning that basically the negative and positive charged particles come out at the same rate. And the way that it does that, it regulates itself by forming an electrostatic barrier, basically, to the negative charged particles on the outside. In the end, what this means is the plasma loses its energy by the fact that it sets up this sheath, this electrostatic barrier, and then particles basically fall through this electrostatic barrier into the material. And so it's literally just impact. Like, so if I'm a surface, I'm going, how is this energy arriving? There's just energetic ions basically dropping through. The height of this energy barrier is set by the plasma temperature, it turns out, and it basically just bombards into the material surface. So that's one way you get energy. It turns out the boundary part of the plasma tends to be at around the ionization potential of hydrogen because it's cold out there. It's not where the fusion is occurring. It's basically the coldest. In fact, if you've ever seen a picture of a fusion device, you'll see an ambient light that's all the way around the edge of it, but you see nothing else. That's because that's where the ionization is occurring. That's at 10 electron volts, which is like 1,000 times less temperature than where the fusion's going on. So say this cold outer boundary about where things are going on. And at 10 eV, it turns out approximately the energy at which the particles will go is something like 5 to 10 times that temperature. So what's actually happening is the particles are dropping through about 100-volt accelerator into the material. And the rate at which that happens basically sets the power. So at 100 volts or 100 eV, This means the charged particle only goes like a couple of monolayers of atoms in it. So it is literally a surface heat, right? That's all. So that's one way energy gets out. So how do you get that energy out? That comes into a surface. This means how do you get it out in equilibrium must be through thermal conduction. So there has to be an object that has high thermal conductivity and hopefully thin, so that you can promote heat conduction and get it out to some kind of a coolant, right? So the typical pictures you would imagine, you get some engineered surface, and then you have a coolant pipe like right behind it, and you make this really thin. The charged particles bombard the surface, and you basically extract it. So it's so now you can see why this is multidisciplinary. By the way, this problem looks like it's mechanical engineering. It's heat transfer, right? It's like the same thing as like how do you get energy out in an internal combustion engine? By heat transfer. It's a really, really weird environment. There's a thermonuclear plasma a couple centimeters away from you. Yeah. The other way to get the heat out of the plasma is in fact photons, because the plasma is composed of negative and charged particles. We already talked about this thing that I said one of the ways we measure what's going on is the release of photons. So stars are being lost by the Stefan Boltzmann law, right? So basically the equilibrium there is set by black body radiation, Planck radiation, which is coming from the surface of the sun, which varies like temperature to the fourth power, right? That's actually why the sun is so stable, because it has such an enormous temperature variation. It turns out there's an equivalent in plasmas as well too, is that plasmas have heat conductivity, which depends the temperature to the 5/2 power as well too. There's very, very strong nonlinearities and all of this. What these tend to be are in fact thermostats, which actually regulate the temperature of the medium around on these things. So in the end, but you're right, is that in fact, the interesting thing, the subject of a lot of my recent research is in fact optimizing or maximizing the allowed fraction of power that comes out as photons rather than as charged particles. Photons are way, way better and it's easy. It's because what's the problem with those charged particles coming in and hitting a surface? And if you got that, see, I can't stop being a professor. It's interesting. They're at 100 electron volts. Oh, what's the binding energy of, you probably don't think of, I think of matter as being basically a collection of atoms and energy wells. Yeah, it's a few, in fact, what vaporization and so forth is just actually surface atoms which get enough energy based on thermal energy distributions to leave the surface. It's like, oh, they're an order of 5 electron volts. So this means the medium of the plasma interacting with this, unless you get the plasma super cold, it actually literally vaporizes the material from, but we have a special name for this, we call it sputtering, because it's actually an atomistic process that there's a finite probability for every ion that falls through it, you eject a particle back up into it, and this means you're going to start remaking the surfaces. Another way to think, it's almost like it's a corrosive medium, but it depends on kinematics, right, around all that. A lot of my research was actually in this area. It's a very complex system itself, just around. So this is why you like photons, because photons they come with energy, but they don't have really, technically they have momentum, but it's not enough to actually cause the ejection of these. So having photons come out, how do you do that? What you want is a lot of inelastic collisions and processes that basically make photons, which typically have photon energies which are like that of the electrons in the plasma, but the electrons are sort of keV, so these are basically X-rays, right? And so X-rays also have penetration distances into normal matter of only submicrons, right? In fact, that also turns out to just surface heat. It's everything. So in the end, what happens after all that explanation, all of this internal the plasma heat, the 1/5 of it, and whatever you put in for external heating purposes, comes out through a surface, through these variety of mechanisms. That's the hardest part, by far. It's because that's all limited by your ability to carry away heat through an engineered material. So this means you must have high thermal conductivity, you want the system thin, you must have coolants in close proximity. Okay, that's already a hard problem. And in fact, But wait till you hear how hard this problem really is, because that's actually not the hard problem of it. Here's the hard problem. It's because 4/5 of the energy comes out as the neutron. So from an energy transfer point of view, this is by far the simplest, much simpler. Remember I told you before, because neutrons have they have no charge. There's other kinds of reactions, but the primary way they lose energy is elastic collisions with other nuclei, which just means the atoms which are in this thing that you put around. We have a name for this. We call it the blanket, because it literally just surrounds whatever fusion place where the fusion goes on. Because they have such large mean free paths. Oh, and by the way, they're undergoing elastic collision. So it's rather, you asked about moderation. It's the same way that you calculate moderation in that sense, is that in fission, you're moderating the fusion of the neutrons so that they go back to room temperature so that they can cause the next fission reaction. In fusion, all you're caring about, you just want their kinetic energy. And then their kinetic energy ends up as heat, because what they're doing is they're undergoing elastic collisions in this medium. So almost always this medium has to be in the solid or liquid phase.
Sorry, Dennis, can you plug it into the fission reactor so you have a stream of neutrons and then maybe it would...
Neutrons, yes. It's called a fission-fusion. It's called there is such a thing which has been looked at by many people. It's called a fusion-fission hybrid. The idea there is you use the high-energy neutrons so instead of only relying on the internal neutrons which are made by the fission itself, you actually have an external source of the neutrons which come in. So you can think of it as a subcritical pile, that namely, if you take away the neutrons from the fusion, the system goes subcritical, and so it stops using power. We can get back into that. You can use it in
It's interesting.
Way.
It sounds to me reversed on the thermonuclear weapon, where it was like the fission would start fusion. Here it's the fusion effect.
Yes. Yes. So you're right. In a thermonuclear weapon, fission starts, and then it makes an X-ray bath that basically triggers the fusion reactions to make energy gain in the systems. Yes. So you're right. It is like the reverse of that. That you use thermonuclear fusion to actually produce those things. I mean, I can editorialize on that. The problem with it, there's some people who advocate for it, but the way that I look at it is that it adds the complexity of fusion into something which is rather simple, which is basically fission. And fission works. Criticality works, and criticality control work. Otherwise you wouldn't have fission reactors, right? And then the fusion person looks at it and you go, oh, okay, great. And now what I've just done is I've added in all of the environmental waste and proliferation issues that come with fission to make fusion work. It's just like, ugh. One of my colleagues described it, it combines the worst parts of both.
Is there a...
Which I always felt was interesting description.
Is there some kind of situation where, for example, you're in space and you can't bring a whole nuclear reactor, so you then bring a small fusion reactor and a small amount of radioactive material and you combine them? So where like some flavor of that, like where you can't, something that's too small to be a nuclear reactor.
Yep, we designed it already. You should come take my class, my fusion design class. So what we designed was a fusion-fission hybrid, for the reason that what we were designing it for was colonizing Mars.
There you go.
Excellent.
Yeah. So just you don't have to bring as much nuclear material, or the size of the reactor can be smaller, and you can turn it on and off, stuff like that.
So it had two motivations. One was, it's unclear about who's going to let you launch things into Earth orbit with a critical nuclear assembly.
SpaceX probably, if anyone.
Well, don't get me started on that one. Actually, my class was this class was a bit of taking apart the mythology of going to Mars and colonizing it, which will not happen if you don't sort out a whole bunch of nuclear issues, it turns out. By the way, solar sucks on Mars because it's a lot further away from the sun. And there's no oxygen to burn. What are you doing, right? And so you look at those things. So it turns out that there is a fuel on Mars for fission. It's called thorium.
But you have to breed it into uranium.
Bingo. In fact, it's a fertile fuel is what we call this. So if you actually expose it to neutrons, it will produce fissile fuel, and that way you can burn it. And that was the idea that this is why we used, and this approach was you wanted a fusion-fission hybrid because you wanted to be able to breed fuel on the surface of Mars after that. So that, along with the launching things which are subcritical from a safety point of view, seem to be a winner. Yeah. There's a whole bunch of other things which come into play like that, like not having everyone die of radiation poisoning on the trip to Mars, which is
because you have to
the
shield
other
yourself from the uranium or whatever it is.
No, it's not from that. It's from the cosmic rays. It's from the cosmic background. Yeah, this is irresponsible actually for a lot of people. A lot of people who should know better actually is that when you look at the radiation exposure that you would get in standard rocketry, it was like there's a reason why we stay in low Earth orbit all the time for all these things. It's for how long? Because once you get into interplanetary space, the problem is twofold. One is solar radiation, which can be very, very extreme, and solar events like coronal mass ejections. And the real big one is the background radiation. So this is like the GeV class protons, which are basically in the background cosmic radiation. Turns out life starts on planets for a reason. It's because, by the way, how do we, the reason that we have a relatively benign environment is because two things, atmosphere and magnetic field that we have around the Earth, which is itself interesting because I have many colleagues who work on those problems because they're related to, it's plasma physics, right? It's charged particles, it's all those other things. So that ended up being actually one of the solutions that we came up with was we thought of this, and we haven't really pursued it more since then, but we actually came up with an idea of having the astronauts live inside of a superconducting magnet.
That's pretty cool.
So what it would do is reproduce the dipole field that we have on Earth, except it's about a million times more powerful magnetic field. But if you remember your electromagnetics, you remember the dipole moment has to do with the strength of the magnetic field and the size of the object. So you can actually approximately make the Earth's dipole moment with superconducting magnets and this thing. And so what you do is you have the astronauts living inside the electromagnets, which is like spinning, basically. And this way they have centrifugal force for gravity purposes. And then the charged particles get deflected around the magnet because of the...
So what are those magnets? Is it like some MRI scale magnets?
It's even higher. That's actually why this is an interesting one. It all came from the idea of using the new magnets that were developed for fusion. So these high temperature superconducting magnets, because they can produce higher...
How many Tesla? Wow,
10 Tesla.
That's impressive. I just visited my friend and they combined like the two MRI magnets for confining plasma at UMD. So it was like already pretty intense to stay next to those magnets. I don't know how the astronauts feel inside those magnets.
Your credit cards get wiped.
No, so actually it's a good question actually, but think about your electromagnetism. If you make a hollow ring and the current is on the outside of the ring, the magnetic field inside gets really small when you live inside the magnet.
Yeah.
So you're living inside the volume of where, because the currents roughly cancel out.
Oh, I see. There will be no currents. Okay.
Is outside.
Yes.
Oh yeah.
So inside is better than outside.
It's not zero on the inside. Yeah. So this is why you basically it's a ring, and then you have the current that produces the superconducting, and the superconductors are on the outside of that, and the current is going like this. So you basically get a toroidal ring. This makes a dipole magnetic field that is super intense on the inside of the ring, but on the in the interior part of the column, it's not zero, but it gets a lot
what
smaller.
happens to all the charged particles inside our body, right? They'll be like the magnetic field would accelerate those processes.
Yeah, it's a good question. Yeah, so it turns out around I think it's about 4 or 5 Tesla, you start to, if you immerse a human being in 4 or 5 Tesla magnetic fields, they start to hallucinate quite badly.
Oh yeah, because we're diamagnetic, I would imagine that would have quite some effect. And at some point you start floating like a frog.
Yes, you start floating. Yeah. Anyway, so you don't do those things. You knock it down to, I can't even remember the number we came. I think we got it down to half a Tesla or something on the inside. That's still pretty high magnetic field, but you're probably okay. It's better than getting all of your DNA screwed up with radiation damage from charged particles. Anyway, yes.
Make a mu metal suit for
something like that. It's like Magneto or something. Yeah. But back to the neutrons. The neutrons are interesting because as the neutrons come out, their average distance between collisions is like large, 5 to 10 centimeters. And then it's an elastic collision, most of them. And so what this means is they basically do energy transfer, and that's just following kinematics. So of whatever it is. But you asked about moderation. Actually, so this is why, like in fission devices, you use water. It's because the neutron is interacting with protons, so it has the most efficient energy transfer because by classical kinematics, right? When the masses are matched, you get the maximum energy transfer possible with that. And it's at 14 MeV, and you need to get it down to like 0.03 electron volts, which is room temperature. So it's actually going around, it's about 8 to 9 orders of magnitude drop in the kinetic energy. So what this means is that it means multiple collisions, scattering collisions, and then on average, each of the collisions, it loses some fraction of the energy. So it's like a power law. You solve this, and it turns out if you send 14 MeV neutrons into water, it takes them about 30 collisions to slow down to near room temperature. And if it's something that has a worse match for a mass, so like iron, it's like 600 or 700 times it has to collide with things. So what this looks like is it's basically bouncing around in this to thermalize. But of course, every time it bounces on something, it's imparting kinetic energy, but that kinetic energy then is in a charged particle, and so it has a very small range. And so it basically just provides local heating. So it basically, in the end, what it just means is that you get volumetric heating from neutrons, which is fantastic, because volumetric heating is way easier to deal with than surface heating. And in fact, the best solution to this is that you primarily want to make this medium out of a liquid. Because if it's a liquid, then what this means is that the direct volumetric heating is occurring in the thing that you're going to transfer the energy out of. So in the end, that's how you do it, right? You get this volumetric heating, and you're pumping a fluid of some kind through it, and then you pump it in and out of the system at a constant rate that exactly matches the total amount of fusion power that you get. So there you go. That's how simple and complicated heat transfer is, but recognize about how nasty it is. One is that it all has to come through one surface, like shit. That's really hard, right? Because geometry is against you, right? Because all heat transfer is surface limited, and you only have one surface. This makes it harder already, right? Because you want high average power, volumetric power, not surface power. But they're linked to each other through the physics of that one. So geometry is harder, and this also means whatever the fluid that you're putting through the system should not interact very strongly with whatever is the containment mechanism that you're using. Like, in one sense, fusion has incredible flexibility because it's the only energy source, that where the working fluid, by definition, like the working medium of the engineered system, has nothing to do with the energy source, by definition, because they must remain isolated from each other. In other words, the blanket has no idea that there's a thermonuclear fusion plasma inside of it, and the thermonuclear plasma has no idea there's a blanket outside of it. So this is cool, because what it means is you can separate the function of these things in important ways, which you can't do like in fission, for example, because they actually interact with each other. And the same thing like in coal and all these other things, fusion, you can separate them. But this also means that you have to keep them separated. You can't let like the blanket like leak into the plasma or vice versa, because you have to keep them fully isolated from each other. The big one then comes though too, so that part's relatively is important, but you also realize right away the challenge of heat transfer is one of the major problems of thinking about fusion power plants, because it's the rate at which you can safely bring out the energy, which is the thing that sets the economics, because that's what you're selling in the end, right, is an energy. But here's the kicker, right? So in DT fusion, you have to do two more things. So one of them is you have to make tritium. And the reason for that is tritium has a 12.3-year half-life. It's produced in the environment. It decays so fast that there isn't any tritium really around on Earth at all. This means that fusion devices have to be self-sustaining in tritium. What you actually are doing is tritium is incorrectly stated as the fuel of fusion. It is absolutely not the fuel of fusion. It is the extra neutron that you add onto the deuterium is like a catalyst basically in the system. And you're using it, it goes right back to your original question, that extra neutron gives you this much higher reactivity. Just like you think of a catalyst in a chemical reaction, you add it in to increase the reactivity. But you recapture basically that catalyst and use it over and over again. In fusion, the catalyst is the extra neutron. And that neutron now comes out and boom, 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 bounces around, but it turns out it has a fission-like reaction, 1,000 barn, with lithium-6. And the neutron actually undergoes a nuclear reaction. It is like a fission reaction, actually, more than a fusion reaction. It undergoes neutron capture into lithium-6 and produces net energy, which is cool. That actually, it's at an energy which is around a quarter of what the whole of fusion energy is. You actually get more energy out of the system. And it produces a helium particle, surprise, surprise, because that's why it wants to release net energy, because the helium is so stable, and a tritium. And then so what you do is you take that tritium, and then you're going to regain that tritium, which is really the extra neutron, and you put it back into the system again. And you keep reusing it over and over again like that. So in the end, tritium is that. So what does that mean? Is that so you're already seeing some constraints, right? This means that this medium must contain lithium at some pretty significant fraction, because what you need to sustain this fuel cycle is that for every fusion reaction that occurs, on average, you must produce at least one or more tritons from that reaction to keep this fuel cycle going, because you have to recapture the catalyst to keep it going as well too.